And here you have it. Welcome back to the next phase of our 8-bit computer building. And I'm quite sure that for some of you who have been following, you're familiar with this module, which is the clock system built with the 555 chip. And now we have here two registers, which is the A register and the B register. And in between them, we have a module which we call the ALU, also known as the Arithmetic Logic Unit. And with this unit, we'll be able to perform arithmetic operations, so addition of binary numbers and subtraction of binary numbers. And these three modules have been realized with the sketch here. So I'm just going to walk you down quickly. So if you look here, we have 274 LS173, and these are memory blocks which contains 4 D flip-flop each, 4-bit D flip-flop in each of this chip. So which is why we have these two here, and they're responsible for the memory of each bit in this register. And you can see that it's all connected back to the bus. And what it means is that we can send in data into this memory unit by controlling the load signal. And here I have my load signal to be this. And we can also send the data out back to the bus, which will be controlled with this transmitter and transceiver 74LS245, which is what I have here. And you can control the load signal with this. This is the load signal, and this can be controlled here with this. And exactly what I have here is similar to what I have. Just exactly what you can see here is the same thing you can see on the A register. Yeah. And today we're going to add some binary numbers, and then you'll see how it works. So, but then the ALU is made up of two chips, 74LS83. And you can see that the ALU unit here takes the input from the A register, and also it takes the other input from the B register, which where 4-bit goes into this chip here, and the other 4-bit goes into this chip. Now, what is chip 74LS86, which is these two chips here? As you can see here, the data from the 8-bit goes into this chip first before going into this chip. And this is exactly what we have here. So you see, the data from the B register is all going into these two chips, and then the data is then transferred to this other two chip, which does the addition. And then you have again the 74LS245 that sends the signal out to the bus system, which you can see here also. Okay, and this component here, this chip here, is responsible for ensuring that we can perform the subtraction operation on this arithmetic logic unit. Otherwise, if we are going to do only addition operation, we wouldn't need this chip. So with this, this chip consists of 4 exclusive OR gates that negates the input value once this signal for the subtract is high. And here you can see the signal for the subtract here. So now it's low, so which means we are going to be performing addition operation. And with the bus, I can control or I can vary the data that goes into the register to perform the arithmetic operation. So, but first, in order to illustrate how this works, I need to show you how the computer performs the subtraction operation. So for subtraction of register A value and B value, so normally the ALU will do only addition operation, but then we can convert the second operand to its negative value, and then we can perform the addition to give us the actual result for the subtraction. So how do we perform the negation of the second value? So we do this by getting the 2 complements. So it's called 2 complement. So what it does is here to do A minus B, you need to do A plus the B complement. So first, the B complement is equals to the first complement plus 1. So in order to do the first complement, so first we need to negate every bit in the value, and then the 2's complement, we need to add 1 to the first complement, which is exactly what we have here. And then you go back here, and now you can perform this operation A plus B complement, which will be the binary number of 25 plus the B complement of 14. And when you do this operation and you perform this addition, you would get this same value here, and which gives you 11 as a decimal number. And now we are going to perform this operation here on this ALU unit. So first I'm going to clear all the data in the register by So as seen here, you can see that for all the registers, you have a load signal. So once this load signal is low, because this bar above it indicates is a negative high, is the negative high signal. So it means that once this value is low, it means you can allow data from the bus to flow into the register. And as you can see, this data in the registers will be updated when the clock signal goes in at the next clock signal. So you can see why I have my clock system here, and my output is this white cable here going to the A register, and it also goes to the B register. So in order to, first I have to clear every data first. So I already have this on the low, and I put it back high. So to clear this register, I need to set it to low and back to high. So you see right now I have 0, 8-bit, all zeros in both registers. And because my subtract signal is low, so which means the ALU is configured to perform addition operation. So which means 0 plus 0 is equals to 0, because as you can see, all the bits are low. So first I'm going to load my A register with this binary number. So it's going to be 0, 0, 0, 0, 0, 1, 1, and 0, 0, 1. So now I've configured the bus to have this data in it. And so I'm going to load this data by setting the load signal to low on the A register. And I'm going to do that here. Yep. So as you can see here, I have 0, 0, 0, 1, 1, 0, 0, 1 as indicated here for the 25 decimal number. And when you look closely, you will see again the ALU already performed the addition operation, showing you that 25 plus 0 is going to give you 25, which is 0, 0, 0, 1, 1, 0, 0, 1. And so now I'm going to load the B register with the binary number 14, so which is 1110. So to do that, I'm going to take this off, put 0, 1, 1, 1, and all zeros. So again, I'm going to activate the load signal to load the data into the register. Set it low, and then I can set it back to high again. So as you can see, I have 1110, which is the equivalent of the decimal number 14 in binary. And now the addition value, the sum of these two values should give you 39 in decimal, and you should get 001, 00111 in binary. And oh yeah, because I didn't set this value back to low, so I need to set this back again, because now I'm having the same value on the A and B register. So to configure that back again, I need to have 001, 1, 1, 001. So it's going to be 00. So I'm going to load it back here again. Okay, so I have the values back again, 000111001, that's here, and here it's still the same value as 141110. And when you look at the sum of the values, you see you have 001, 00111, which is exactly the same as what we have here, 001, 00111 for 39. And so in order to perform the subtraction operation, all I need to do is to set the subtraction signal to high. And what it's going to do is going to convert each bit to give you the first complement. And because this signal is high, it's going to take this high into this point. So this is where we do the 1 addition here. So it's going to take this 1 as high, and it's going to put it into this chip, and it does the conversion to give you the 2 complements of the operand, and then it performs the addition in these chips and gives you the output here. So to do that, I have to set this signal to high, and now it performs the subtraction operation. As you can see, now I have 0.0001011, and this is actually the solution for the subtraction. And in a nutshell, this is showing how, this is just to show how the ALU performs operation in the computer. And we've been able to demonstrate that using the 8-bit computer on our breadboard. And the next phase is we're going to introduce the RAM component for our computer. And I hope you like that, and I look forward to make this a reality. So thank you for watching, and you can share this video with your friends who are studying computer science, and maybe it helps. All right, so see you some other time. Bye-bye.